All right. All right. We are going to talk about basically the different ways that you can find exoplanets. There are five methods. Really, only one of them works very well. But in the early days, they came up with several methods that they were trying out to try to see if they could do it. And I'll talk about the transit method uh, here in the presentation, which is the most prolific one. It's just found thousands. And I intended to go through and update this slide deck this morning with numbers, but I didn't get to it, so I'll just update that as we go along. But just keep in mind the one cool, exciting thing and the one frustrating thing for present presenters about exoplanets is we're finding them all the time and we're adding the numbers all the time. So there's no presentation is ever going to be up to date on it at this time. So we'll just do the best we can with it. What you're looking at here is they talked about in the video 51 Pegasi b was the first exoplanet that was found. It's a pretty big planet. It's way bigger than Jupiter, and it's very close to its star. Only Mercury takes 88 days to orbit around the sun. This takes 3 days. We have found planets that actually take half a day to orbit their stars. They're so close. I mean, it's just hard to imagine a planet being that close to its star and surviving. And what's happening to 51 Pegasi b, now this isn't because we have pictures of it or anything. There is circumstantial evidence that supports this kind of thing, and also logic. It's a gas giant, and it's being boiled off the atmosphere. All of the planet is an atmosphere. Its atmosphere is being boiled off by the heat of its star because it's so close to it. And so pretty soon it will boil off to nothing. I have an extra. I'm not going to have you guys do it this year, but I have had students work on it in the past. Based on the rate that we have figured out that it is losing mass as it goes around this star and it gets boiled off, how long will this planet take before it's no longer there? And it turns out to be like 5 billion years. But it's an incredible amount of material that's being boiled off. It's like 700 tons every second is being boiled off. And so it's a really big planet with lots of mass. And so that's kind of a surprising result that it's going to take that long. But anyway, that's just obviously an artist rendition of it. And that's kind of how we picture 51 Pegasi b looks like. We have found five. This is one of the things I needed to update. This slide says this is the only Earth-like planet that we have discovered. We have discovered five that are in the habitable zone. Now, just to be clear, the habitable zone is the distance from a star that water in liquid form can exist on a planet. Like Mercury is too close to the sun, the water would just boil off and be gone. Out past Mars, it's too cold. There's not enough energy from the sun reaching out there to keep water as a liquid. So any water out there is frozen unless there are circumstances other than the sun involved. But so that actual line where you go from liquid water to frozen water is called the ice line. And so Jupiter and beyond are all beyond that ice line. And Mercury only Venus, Earth, and Mars are in our habitable zone, and the Earth is right in the center of it, right in the perfect spot. Venus is a little bit too close, and so it gets lots of energy, and that really speeds up that. What's the effect? Greenhouse. Yeah, greenhouse effect. Yeah, that's causing all the atmosphere and pressure and how hot it is and everything. And Mars is on its warmest day about the temperature of the Arctic. However, in its spring, it does have seasons. In its spring, there are places on there where liquid water appears to exist. it seems we have actually photographed running water on some parts of Mars. Uh, that is definitely in the habitable zone. So this is an artist rendition. We have no idea if that's exactly how it looks, but based on its density, we have an idea of how much water and how much land is on it, and so they would, kind of draw it to the right proportions and make it look interesting. All right. Then it says as of 2017, over 3,000 extrasolar systems have been found. Well, as of this year, over 8,000 have been found and confirmed, and 5 of those are Earth-like planets in the habitable zone, which is pretty exciting. Um, the farthest one away that we have found is 300 light years. The closest we found is 4 light years. So 4 light years is close. It would only take us 75,000 years to get to it at our current speeds. But oh well. So it's going to be a while before we actually know what these planets actually look like and everything. We just don't have the technology to get there. All right. So there are several kinds of planets. We're kind of narrowing these down. Right now, if you study science for any amount of time, you realize science goes through stages. It goes through, the first thing that science starts doing is classifying things. How do we classify stuff? When I was in school in biology, there were 2 kingdoms. How many are there now? There's 5 or 7, right? Geez, guys, you took biology a lot sooner than I did. You don't even remember how many kingdoms there are? Well,
like 70 in biology.
Yeah, okay. So I think there's some, yeah, a whole lot more than when I was a student. It's not because, we found so much more stuff. We've figured out how to classify things differently because we've gotten a little more precise. Well, we're still in that stage with exoplanets of trying to identify different categories of what they are. When we only had a few hundred, it was kind of hard to really know what to classify them as. Now that we've got over 8,000, we're starting to see maybe some patterns develop in the kinds of planets that exist. But right now, it doesn't hurt to look at them in these 5 ways. Terrestrial planets, which are any kind of small rocky planet. Mercury, Venus, Earth, and Mars are all terrestrial planets, even though Venus and Mercury and Mars have nothing terrestrial on them. Technically, they're like the Earth. They're mostly just rock. They're not gas of any kind. They're gas giants. Those are the kind that are out beyond the ice line, like our planets are. They're just normal gas giants doing their thing. But then there's hot Jupiters. Those are the ones that are really close, like 51 Pegasi b, that are just getting fried. I would say boiled by their stars because they're so close in. Hot Neptunes are Neptune sized. If you kind of look up here on the wall, you'll see Jupiter's really big, and Neptune and Uranus are not quite as big. So we've got some that are not quite as big, and they may be mostly water, like these 2 are. They may be mostly water, and they're in close, and they're getting boiled as well. It used to be that we used to call these Neptune-sized planets Earth-type planets because they're only 20 times bigger than Earth. And I'm like, yeah, only? Can you imagine weighing more than 20 times what you weigh now? That's not very Earth-like to me. So, and they're kind of coming around that. Now that they found the 5 that are really close. One of them is like twice the size of the Earth. One is slightly smaller than the Earth. It makes a little more sense that we can call these things something else. And they're actually probably not calling them hot Neptunes. They're just calling them planets. And then there's pulsar planets. Planets found around pulsars. Pulsars are neutron stars. And they're called pulsars because based on the physics, they have a huge, highly energetic stream of particles coming out from both their poles. And they spin. A lot of times they don't spin like we do around our pole. Their poles spin around. I don't know how to say it, but their poles are doing the spinning, and so those highly energetic particles only hit you every so often. Here on Earth, we detect them. That's how we detected the first pulsars. Was we've got radio signals that go beep, 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 or sometimes they are spinning so fast that they're doing thousands of those a second, and they sound just like a buzz. So those are spinning around, and they are the result of a supernova, a star that collapsed in on itself and exploded, pushing together in its core, pushing together the electrons into the protons, creating neutrons. That's why it's called a neutron star. It's just all neutrons. And that supernova explosion would have obliterated literally, just atomized everything within 20 light years at least. So how are there planets there? But that's interesting. But that was actually how we found the first planets. We didn't know it at the time, but they were there, and I'll get into that here in just a little bit. We have a Kuiper belt, and we have an asteroid belt, and it turns out that most solar systems have those things as well. There are areas where they just have fragments of stuff orbiting around in a field. There could be one of them, there could be two of them, or whatever, but we have observed that in other stars. So we're not just finding planets, we're finding other characteristics that fit just like our solar system does. We have pictures of planets forming. This is thanks to Hubble. We've got some really interesting pictures. Now, these are extremely rare to see these, but if you look at, I can't see over there, but if you look at the orange round ones here, they're showing a star that is just poofing into existence and blasting out its dust and gas from the pressure of the explosion of it starting to ignite in diffusion. And what's left behind are these little dots, and the dots are planets. And in this other one here on the far right, these two pictures, you see disturbances in what's called the accretion disk around a star. Well, those disturbances are there because a planet is forming right there. So these are not fully formed planets, but this is the birthing process of a planet in a solar system. So it's pretty exciting that we actually have pictures of that. Okay, and actual exoplanets, how do we really discover them and know that we found them? Well, there's 5 methods. And like I said, really only 1 or 2 of them are working. All right, so 2 are exactly alike. We just use different methods to detect them. Astrometry, that's pronounced astrometry, and radial velocity. Now, I'm going to talk about each one of these things as we go through in more detail and explain what it all means. Then there's the transit method, which that is the most effective way that we've had for finding exoplanets. Microlensing, that's used for so many things we'll talk about, and pulsar timing. That pulsar timing is the only way to find pulsar planets, the ones that shouldn't exist, but they do. All right, so the astrometry method, and they talked about this in the movie. They didn't talk about this method, but they talked about the process of a star doing a wobble, right, as a planet goes around it. And our sun does a wobble as well. And it wobbles a lot because there's a lot of planets going around it. So it's a very complicated wobble that it has. The thing is, even with all these planets and stuff going around it, and keep in mind, the sun is about 1 million miles across. It only wobbles about 80 miles. So there's only, it's really not detectable. It's hardly detectable from Earth, let alone from somewhere else. But astrometry method is the idea that you can calculate an exoplanet is there based on observing the star wobble. And the success of this method is absolutely zero. It has not found any exoplanets whatsoever. So uh, the pros of using this kind of method, you can look at a lot of stars with a telescope at once. The cons is it really doesn't work. so so I think they've pretty much abandoned trying to do this kind of method until we get instruments that can detect this tiny amount of wobble. But here's an example. As you look here, if you're really close to the star, it's easy to see the wobble. But as you get farther and farther away from the star, you cannot detect the wobble whatsoever. So it's not a method that we really want to use. Now, what they talked about in the video was the redshift blue shift, the Doppler effect. And here, and it's really tiny. It also is hard to detect, but turns out to be much easier for our instruments to detect than direct measurement. And here's an example. Up here at the top is the normal unshifted spectrum. The black lines are the absorption lines, called absorption lines, and that's how we identify the different chemicals that are in the star. And we can identify that this is every star, that's like a fingerprint for every star. They all have their own unique spectrum. And so we're looking at the star, and you look down here, it's red shifted. It's kind of shifted to the right, towards the red. If you look closely at that, you can see that. And then down here at the bottom, it's shifted towards the blue. As it shifted towards the blue, it means that that star is wobbling towards you, and then it's wobbling away from you and becoming red shifted, and then blue shifted, red shifted. So we can look for that and determine whether we think there is an exoplanet there. As always, there's all kinds of explanations for why that could be wobbling. So this is not definitive. None of this is definitive proof. We have to verify by other methods. All right. So just showing. Okay. Oh yeah. I want to show you. If you have a planet going around you in a nearly circular orbit, you're going to have this just very nice sine wave, very nice and smooth. But if it's highly elliptical, you're going to get these kind of razor, saw blade type of graphs showing the movement in the red shift and the blue shift, because it'll probably shift away from you or towards you really fast, and then at the other end will be really slow because of the highly elliptical orbit. All right, so the pros. It still can't be used on faraway stars. The shift is just going to be too small for us to detect. And you can only look at really one star at a time. So it's a very slow, tedious method. You can only detect stars that are moving a lot. Even though the shift in the spectrum is small, the stars are moving a lot. So again, this is pretty much a method that we've abandoned. We don't really use it anymore, even though they really touted it in the video. It's not really an efficient method for finding exoplanets. Now, the method that's really good is the transit method. Now, we're talking about very tiny differences in a star's light. As a planet goes in front of it, the star dims just a little bit, right? Because some of that light gets blocked. I mean, we're talking about 1/10% of the light or something like that, really tiny. But it's enough that the instruments that we have, especially ones spaced out in space, are very good at detecting these things. This is another hot Jupiter, and we can see that there's actually a trail of gas behind this thing because of the way the star gets dimmed as it goes in front of it. And so we can tell that, yeah, atmosphere does get boiled off. This is not a picture of it. This is an artist's rendition. But when we look at the numbers of the luminosity of the star and stuff, we can tell what's going on. All right. So the thing about the transit method is It has to be just right. If the planet is orbiting the star vertical to us, it's not going to come between us and the star, and we're not going to get any kind of dimming of the star. It has to come horizontal, exactly between us and the star for us to see it. Does that make sense? Okay. Um, so that's that's a limitation. Not every solar system out there has planets orbiting in the right direction. So we can only detect those. Um, let's see. Yeah. So if you are looking at how to tell if it's a planet as it's going across, when the planet, if you look at position number one, there's nothing in front of the star. The star's luminosity is right here at at the peak brightness, right where letter number one is. You got this straight line going across basically because that's what the luminosity of the star is. As the planet goes in front, at say position two, that starts dipping just a little bit because it's starting to more and more block the star until in position three it's completely in front of the star, and as much of that star's light that's going to be blocked is blocked, and it creates kind of a flat surface down here on the graph as it transits across the front of that star. And then when it gets to the other side, we could have put a position four here. It will do just the exact opposite. As the star goes off, it blocks less and less light until it's completely passed, and then we're back to full luminosity of the star. So it's a very telltale sign of a planet going in front of a star is this kind of shaped dip in the luminosity of the light. We can tell some things from this. Next block, you are going to actually work with some data that will help you determine the size of the planet and how far away from its star that it is. You will do a tiny bit of math. You'll have to do a square root. That's about it. And that's it. That's the only math you'll have to do because the universe is so uniform that we can actually know things just from tables and graphs without having to do any math. So one of the things to notice here, we got at the top, we got three different size stars, but we've got the same size of planet going in front of them. And so they each have a different graph of the light getting dimmed. This first one here, the light doesn't get dimmed too much because the planet isn't blocking too much of that huge star's light, right? It's a small percentage, so it doesn't dip too long, but it dips for a long time. At the bottom, that line is very, very long because it takes so long for it to transit across the front of that star. Clear at the other end, that small red star, same size planet, but it's bigger in proportion to that star than the first one. So it blocks a whole lot more light of that star than it does the big one. So you see a bigger, deeper dip in the light that's blocked, but it doesn't take as long to get across. So you can tell that number one, this is at this end is a bigger planet compared to its star. If we know the brightness of the star and how much it dips, we can calculate how big that planet is. All right, that's not something I would have you guys do. We've got a way to do that. That's fairly simple. At the bottom, you can tell if you know the size of your star. You can tell whether you have a big planet or a small planet too. You can also determine that because again, the bigger the planet is, the more of its star's light it blocks, and the less time it takes to get across that star. It takes a big planet a lot less time to get across the front of a star than a small planet. That makes sense? Okay. Hang in there. We're getting close. All right. We got a couple of methods to go, but they're not as good as this, but they're worth mentioning. All right. So the transit method, pros and cons, can be used on just about any star that there is. Uh, it can detect small planets. Our instruments have been able to detect transits of planets as small as Mercury going across their stars. Um, it can actually determine, based on the spectrum that they take of the atmospheres of these planets as they go across, we can determine if what their atmospheric composition is. This is one of the things that James Webb Telescope is specifically designed to do, is to look at the atmospheres of these exoplanets and determine if there's methane in it. If there's methane, it doesn't mean that there's life there, but it's a good chance that there is, because life as we know it all produces methane as a waste product. All right, the cons: we can't detect all of the solar systems out there because not all of them are oriented in the right position to have that planet go between us and the star. But we have found 8,000 planets this way. We've done it with a satellite, well, I should say a probe called Kepler. It's a telescope that we put out there for this specific purpose. It would scan the sky 10,000 stars at a time and take data, and just keep doing that through the years. And we would gather data and be able to make these what's called light curves of the light dips and things like that. And that's been responsible for almost all of the transit discoveries that we've had. It kind of died a couple of years ago, quit working like it's supposed to, lost some of its abilities, and so it's been moved to a different science. But we have a new satellite up there called TESS, which is even more accurate than Kepler, and so we should be finding many more from that telescope. All right. Fourth method is called gravitational lensing. We use gravitational lensing in astronomy for many things. We can find galaxies that are behind other galaxies because the light gets bent by the gravity of the galaxies in front. We can I'll show you a picture here in just a second of something like that. We can actually use a star that's close to Earth to look at a star that's far away from Earth. And as that star is far away from Earth, passes behind the star that's close to Earth, as you see in these pictures, it actually gravitationally lenses, and we see there's a point where we will see that star twice on either side of the star. The light coming from that far star gets bent around the close star and creates two little dots on both sides. Now, the way gravitational lensing can work for exoplanets is if there's an exoplanet around that far star, its light will get split as well, the light that it's reflecting, and we might be able to detect that little tiny bit of deflection. It's not a very good method. We haven't detected. I think we've detected a couple of exoplanets, so it's not useless, but it's not very efficient either. This is what it would kind of look like. Now, this is a galaxy being microlensed around another galaxy. The circle there is a galaxy that's far away, and believe it or not, it's directly behind this bright that's actually a galaxy right in the center. It looks like a star, but it's a galaxy right in the center. And that's what gravitational lensing looks like as light gets bent around another galaxy. So we'll see that with stars and with exoplanets as well, if there's enough there for us to detect. All right. So the pros is we do have instruments that are sensitive enough to detect these kind of things, but the chances of a star going behind another star perfectly for us to do this is astronomically small. literally. So we've only had a couple of instances where this happened, and it worked out that in both instances they had exoplanets around them. So that was pretty cool. All right, pulsar timing. This is now where those the way to find conventional exoplanets. Pulsar planets that should not exist are found by seeing a wobble in a pulsar. As the pulsar, I told you about the particles being shot off, and we detect them, and we hear our radio signals would convert it to a beep, 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 or a buzz because it's going so fast. Well, there'll be a change in that sound, like the train horn change pitch. Well, the pitch of that sound will change because we'll get a different wavelength as that pulsar wobbles. And that's how we discovered the first two exoplanets. We had a pulsar that had this variation in its radio waves, and we're wondering what causes that. And it wasn't until we found another exoplanet that we could actually detect around a star that we said, maybe those are planets, but how could they be? But it was confirmed that, yeah, those are planets around that pulsar. So how do they form? We don't know. It's just craziness. All right, so the pros are we don't understand why the planets are there. I don't know why that's a pro, but we don't understand why the planets are there, but we can find them. They may be easier to find than others using that kind of method because the pulsars have a really big beacon to tell us. The cons are it only works for pulsars and it's very rare because it's rare that a pulsar's beam is pointed directly at the Earth. So we get this radio reception. Don't know, and I don't know. Talked about it. Don't know why those planets are there in the first place. There should be none. All right. The last way. There's 6 ways. I think I said 5. There's 6 ways, and one is just taking a picture of the planet, taking a direct image. Here's one of only 2 or 3 that are in existence. You can tell this is a very big planet, and the star is actually very close to Earth. And this is just extremely rare to be able to get something like this. The conditions have to be just right. You have to have just the right equipment. And you're not going to see this on stars that are far away at all. So it's an extremely rare event. So the pros of it is there it is. That there's a planet. You can see it. You don't have to infer it from measurements or anything like that. Boom, it's right there. But the cons are it's virtually impossible to do. The fact that we have any is pretty much a miracle. All right, that's it. That's the all of the ways that we use to find exoplanets and whether they work or not, basically.